Gaston Naessens, what is a somatide?
A somatide is a basic living particle. It is indispensable to life. We find it in both the animal and the vegetable kingdoms. Without it, cellular division can't take place. It is polymorphic. We were able to grow it in a culture, and that's where we observed its polymorphism in 2 cycles. First, there's a microcycle, during which the reproductive hormone that permits cellular division is developed. This cycle is stopped by inhibitors in the blood and during certain illnesses, including degenerative diseases. This cycle, this microcycle, in 3 stages, keeps going and becomes a 16-phase cycle. We're going to demonstrate all this for you in just a little while. But to answer your question, the somatide is an indispensable element to life.
How far back do your observations go?
In 1949, when I was working in hematology, I had the feeling that I wasn't seeing everything there was to see in blood. I saw something moving, but I didn't know what it was. The optic methods available to me fell short of what I needed. I tried to do better, to delve deeper into what I could see. First of all, I concentrated on the question of optics. I went to Germany and worked with German artisans who helped me tremendously. And then a quandary arose. We could work either on the lens aperture or on the wavelength of light. All the large optics companies of the world were working on the numerical aperture. So I didn't have much of a choice. I concentrated on the problem of light wavelengths. That's how I perfected a system that gave very worthwhile results, and which enabled me to develop a microscope that allows us to see this famous particle. Little by little, I was able to observe it, and I extracted it from the blood. I was able to isolate it and grow it in a culture, and that's how I established its polymorphism.
What do you mean by somatide orthobiology?
The very etymology of the word orthobiology indicates that it's a kind of biology that is adapted and tailored to the somatide theory. It's impossible to understand orthobiology if you don't understand the somatide theory. But to understand the somatide theory, you have to have the proper means of observation, and you especially have to understand the basic principle of the somatoscope. Everyone is familiar with the electron microscope. Everyone is aware of the possibilities of the electron microscope, which magnifies more than 400,000 times with a resolution of 50 angstrom. With the electron microscope, you can work on dead tissue, fixed tissue, while with this microscope, the somatoscope, I can see living cells, follow their development, their polymorphism. I see it as a link between a regular optic microscope and the electron microscope. I think this somatoscope is filling a gap. Without it, it would be very difficult to conceive of the somatide theory. Many people have worked in this direction before I did, but they saw things in different ways. They concentrated mainly on chemistry. Some also worked in optics, but there were some incredible characters. They called one the noon lunatic. I think it was Émile Doyen back in 1911. He said he could see living particles in plasma, but that he saw them only in May, June, and July at 12 noon. He saw them move, so he was treated as though he were crazy. But that story takes a completely different turn if we recall that at that particular time, the sun's rays reach their zenith and contain a lot of ultraviolet light. Since ultraviolet light is much shorter and its wavelength is much shorter, he could then see what couldn't be seen at other times. The principle is somewhat similar, I think. However, instead of just using daylight and waiting for noon to come in May or June, I can create the same conditions electronically with ultraviolet rays and with various kinds of mechanisms. By decreasing the wavelength of light, I can increase resolution and therefore see particles that would otherwise be invisible. The principle underlying this device is an increase in the frequency of light. Two light sources, an incandescent light with a wavelength of 3,300 angstrom and an ultraviolet light with a wavelength of 1,850 angstrom, begin to pulsate, producing a third wavelength. This wave passes through a monochromatic filter that produces a ray. The ray is subjected to a magnetic field and split into parallel lines by the Zeeman effect. One of these parallel lines enters a Kerr cell where its frequency is increased. This light source, which is invisible to the naked eye, analyzes the sample to be studied. For more than a century, the traditional method of examining blood has consisted of smearing it onto a slide, fixing it, and staining it to determine the tinctorial affinities of the elements it contains. On the left, we can see blood prepared according to this method. We can identify the red corpuscles, white corpuscles, and platelets. This is dead blood. On the right, we are seeing blood through a somatoscope. This is living blood, examined within 10 minutes after it was drawn. We can see red corpuscles, white corpuscles, platelets, and somátides, which we couldn't see on the fixed slide. There's a lymphocyte. You can see the edge and the large number of somátides. The red corpuscles are absolutely normal. Here we have a monocyte. We can clearly see the activity taking place in the cytoplasm and also the large number of somátides. Down on the bottom left side, we see a platelet. Here's a very active monocyte. At this enlargement, its cytoplasm and the motility of that cytoplasm can be seen very, very clearly. We also see a large number of somátides. Over here, we have another polynuclear neutrophil that's engaging in phagocytic behavior. We can also see intracellular inclusions when they're present, as well as the advanced forms of the somatide cycle when they're present.